All right, so let's find the basis for the subspace S, which consists of some polynomials, degree 2 polynomials, at squared plus bt plus b, where a and b are real numbers, and this is a subspace of P2, all polynomials of degree 2 or less. All right, so we have to find a basis, and a basis, again, is a set that does two things. It spans a subspace or vector space, and two, it's linearly independent. Now, spanning just basically means that when a set spans a vector space or a subspace, means that any element of the subspace or the vector space can be written as a combination of those things inside the basis set. And then linearly independent means that any of the vectors or elements of that set that's we say spans can't be written as a combination of the other ones. Okay, so they're like independent. One doesn't need the other. All right. So how do I do that? So as I said, it's a set. That's what we're looking for, which means that you have to start by finding some vectors here. Now, if you look at that set, at squared plus bt plus b, you can rewrite that expression as follows. You can write it as a times t squared plus, and then I'm going to factor the b out of the bt and the b, and you get t plus 1. Well, I'm looking for, my objects are members of this vector space. The vector space is P2, okay? So, which means they're polynomials. So I have one polynomial with the t squared, and I have another polynomial with the t1, t plus 1. So I'm going to say that my set that I claim will span this space, let me call this set big B here, it's going to be t squared comma t plus 1, right? And we showed that it's a spanning set. These two elements, t squared and t plus 1, will span the set S, because a times t squared plus b times t plus 1, a is a real number, it's a constant, times t squared, and b is another constant times t plus 1. And when you put a constant times two vectors and then add them together, or whatever number of vectors, we're doing a spanning set. And this right here describes everything over here. Okay, so we found the two vectors, just to summarize, that when you multiply by constants and add them together, describe the set S. Okay, that's what we found. So it's t squared and t plus 1. So these are my vectors, which I claim are a basis. They do span the set S. However, when you're showing something's a basis, I said, you have to show that it's spanning and then it's linearly independent. Okay, well, how do I show it's linearly independent? Well, if you take a linear combination of these vectors, so some constant times t squared plus another constant is t plus 1, and you set it equal to the 0 vector. However, in this case, the 0 vector is a polynomial, and always remember that when you're talking about the 0 vector, we just don't mean 0 as the number. It means whatever 0 is represented as in the space that you're working with. In this case, this vector space is polynomials, degree 2. So 0 is like saying 0 plus 0t plus 0 times t squared. And if you went ahead and distributed the c2 here, this is what you'd get, and I still set it equal to that stuff over there. And if I equated like terms, this would equate to this would equate to this, and then this would equate to this. So if I did that, I would get that C2 equals 0, and then C1 would equal 0. So I am equating the coefficients. The coefficients are C1 and C2 and 0. And therefore, because these coefficients are 0, t squared, the set B, t squared t plus 1 is linearly independent. Yeah, and I apologize, I didn't do a great job here of like writing this part out when I have the C1 equals 0. I should have made that a little, I think, cleaner, a little more ordered, but anyway, organized. So sorry about that. But anyways, we've shown that this set is linearly independent and that this set spans. So therefore, the set B is a basis for our set subspace S of P2. Okay, thank you for your time.